All right, welcome to part 6, chapter 27. Let's not forget what we're working on here. So we're working on the last section of chapter 27. We're looking at RC circuits. So we'll go back to figure 2715. Figure 2715, and just by way of review, we had an EMF, we had a switch that can swing through either position A or position B. Here's a switch. And that part of the circuit's going to be connected to a resistor and a capacitor in series. Resistor, capacitor, an EMF, and a switch. So we already looked at the charging up scenario. We looked at when switch was in position A. So we looked at this configuration. That was the charging regime. We looked at the charge per unit time on the capacitor. We looked at the current as a function of time through the circuit. And we looked at the voltage on the capacitor as a function of time. Voltage across the capacitor. So what we're gonna look at now is the discharging event. And so in that case, right, we're gonna move the switch from position A to now position B. And now this is going to be the discharging regime. Okay, so let's redraw that circuit. So essentially we're looking at that circuit now. So let's just redraw that and simplify it. So what we have then is we have a resistor and a capacitor in series. The capacitor is charged. This is the resistor. Here's the capacitor. And we want to look at what happens now with the charge on the capacitor as a function of time, and we can also look at the current as a function of time. We could look at the voltage across the capacitor as a function of time. We could also look at the voltage across the resistor as a function of time as well. Okay, so now let's use Kirchhoff's voltage law. Now there's no seat of EMF in this equation, or in this circuit now. So we have just voltage drops, no voltage gains. Charge is going to move this way. Remember that the voltage across the capacitor is going to be the charge divided by the capacitance. The capacitance is a constant, so as charge leaves, the voltage is going to decrease over time. And naturally, as the charge flows through this resistor, it constitutes a current. There'll be a voltage drop across the resistor. So Kirchhoff's voltage law then, Kirchhoff's voltage law looks like the following. It's going to be negative voltage across the resistor minus the voltage across the capacitor is going to be equal to 0. We can get rid of the negative sign, so we have VR plus VC is equal to 0. The voltage across the resistor is going to be the current going through it times the resistance. And the voltage across the capacitor is going to be the charge divided by the capacitance. Again, charge is a function of t as well. We will recall that I as a function of t is going to be dq dt. We can substitute that into the Kirchhoff's voltage law expression. And then we're going to have then dq dt times r plus q over c is equal to 0. Or we have dq dt plus q over rc is equal to 0. Once again, this is a first order differential equation. It's even more special since we have a 0 on this side of the equation. It's also what is called homogeneous. So it is a first order homogeneous differential equation. And the solution of this is rather simple. Q of t is going to be equal to some Q naught e to the minus t over rc, where Q naught is the charge on the capacitor at time equal to 0. Now, if you, for those of you who want to dig a little bit below the surface here, if you actually want to prove, right? If you want to prove that Q of t is a solution, then just plug it in. Just plug into the differential equation above. Okay? Just plug it into that differential equation, and you will be able to prove that it's a solution. Okay? So, so now, given that we believe that this is a solution to that differential equation, then we can go about our business of solving for things, right? So if you wanted to know what the current looked like, so the current as a function of time is equal to the first derivative of charge with respect to time, right? And that's going to be equal to negative 1 over RC e to the negative t over RC. Okay. Well, let me just think about this for a second here, okay? Just for a second. So what negative sign might be bothering you, okay? And so what it really says, let's go back and look at this, right? So that negative sign is just telling you that the charge is decreasing on the capacitor as a function of time. And other than that, it really shouldn't bother us, okay? If for those of you who had general chemistry, you might remember the rate equations for reactants normally carried a negative sign, again indicating that the reactants were disappearing as a function of time. And the same goes here. So the current, though, in magnitude, right, the current's going to be equal to 1 over RC e to the negative t over RC. And if we were to plot that up, this is time, this is current, then what we have here, this is a Q naught. I forgot a Q naught here, people, right? So, yeah, so there's a Q naught. I forgot that constant. So, and I noticed that because of the units, right? Because you know that so if you were to look at the units of this, that's why units are so important, right? And I automatically knew that something was missing there. I could easily go back and find it, right? So Q naught has units of coulombs. RC has units of seconds, which you proved in one of the last discussions. And so then what you have is Q naught over RC is then units of coulombs per second, which is an amp. Okay, so things work out. So quickly looking at units is really a great big help. So the initial current then is going to be Q naught over RC, and then we're going to have an exponential decrease. Again, this is going to follow a exponential decline, e to the negative t over RC. And so the bigger RC is, the longer it's going to take for that circuit for that capacitor to discharge. The shorter RC is, the quicker the capacitor will discharge. Okay, and there's some problems that I assigned that will get you to look at that, right? Anyway, RC is what's called the time constant. So RC is called the time constant. And so when time is equal to RC, then what happens? IT is going to be equal to Q naught over RC e to the negative t over RC. We can actually write this in the following way. So this is going to be IT is going to be equal to I naught, right? Because Q naught over RC is the initial. This is the current at time equals 0. And we can just call that I naught, e to the negative t over RC. So when t is equal to RC, this is e to the negative RC over RC, which is I naught, e to the negative 1 which is then I naught over E. And so that time constant now is when the current has decreased to 1 over E of its initial value. And so I'll let you figure out what that is numerically, right? So IT when t is equal to 1 time constant, it's going to be equal to I naught times 1 over E, and you can calculate what that is. Okay, so that will tell you a little bit about how far the current decreases in 1 time constant. Okay. And there's other things associated with exponential decreases as well. Sometimes one can talk about a half-life, and that's usually discussed in terms of radioactive decay. But we won't discuss that here. So anyway, people, that puts an end to Chapter 27. I would like you to go back and read the section on capacitors in series and parallel in the chapter on capacitors. And I want you to notice the relationship. Notice the relationships between capacitors and resistors in series and parallel. Okay? Beautiful. All right. We'll start magnetism. So keep an eye out for those lectures, which hopefully will start to be going up this evening. So take care, folks. All right. Talk to you later. Bye.